All right, so today we are, so let me say this way first. So good evening, welcome back to College Algebra. We're going to talk about 1.7 today. We're going to be talking about piecewise functions and symmetry. We talked a little bit about that before, but we're going to get into it this time and hit all of that. So I'm going to tell you my bedtime stories. All right. So the first thing we talk about is symmetry here. That's one of the things they I'm bringing up here is symmetry. And functions can have even function, and odd symmetry. So odd symmetry. I think I spelled symmetry wrong. And even function, and even symmetry. All right. So, or I should say odd functions and even symmetry, even functions. Let's go with that. So we have odd functions and even functions. They have different kinds of symmetry. The even ones are a little bit easier to see. Okay, so we have even functions. These are symmetric about the y-axis. Okay, odd functions. These are symmetric about the origin. Now, functions, like unlike numbers, functions, like numbers are going to be even or odd, but there's no rule for that for functions. You could have functions that are neither, and as a matter of fact, most functions, a lot of them are neither. So no symmetry, that's entirely fine. Okay, they're not even or odd. And there's one class of functions that are both. Okay, they're even and odd. So let's talk about what they are. So let me give you an idea of what an odd function is. So let's go with f of x is equal to 1 over x. This is an odd function. I mean, f of x equals x cubed also is, and anytime you're going to see an odd number up here, that's also going to be an odd function. Okay, if you have nothing else. All right. So let's see here. Let's draw a little t-table first. All right, and then see what we're going to have. So I'm going to come down here, and let's go with -4, -3, -2, -1. I'd say 0, but I think we're going to be in trouble with 0. So 1, 2, 3, and 4. All right. So we're just doing 1 over x for these things. Okay. Let's start with the positive side because those are pretty easy. Okay. So what we're going to say here is f of 1, right, is equal to 1 over 1, which is equal to 1. Okay. F of 2 is equal to 1 over 2, which is 0.5, 1 over 2. F of 3, 1 over 3. And f of 4, which is 1 over 4. All right, zeros, we'll just write that in as undefined because we don't have a value for that. But let's look at this. So what I want you to look at is f of 1 is 1. F of -1 is 1 over -1, which is -1. Okay, so I want you to notice the x, 1 to -1, and then the y, 1 to -1. F of 2, right? F of -2 is equal to -1 over 2. So we put a -2 in instead of a positive, and we got a -1/2 instead of a positive 1/2. Same thing is going to happen for f of 3. So if I put a -3, we get -1/3. So it's almost like if we put the negative in here, the negative comes out over there. All right, and then f of -4, we're going to have -1 over 4. All right, so the rule we're looking for is a function is odd if f of -1 is equal to negative f of x, or f of negative x rather. f of negative x is equal to negative f of x. So here, we have 1, 1 and 1, and then negative 1, negative 1. We have 2, look at negative 2. We have half, negative half. 3, negative 3. We have third and negative whatever 3. Let me show you a different one. Okay, I'll let you guys can play with this one. Okay, but what about this one? All right, what if we have something like f of x is equal to x over x squared plus 1? All right. So for this one, okay, and again, maybe we'll just do negative 3, negative 2, negative 1, 0, and then we'll do 3, 2, 1. Okay. So if I want to deal with f of 3, all right, what we're going to be looking at here, we have 3 over 3 squared plus 1. So it's going to be 3 over 3 squared is 9, 9 plus 1, 10. What about negative 3, f of negative 3? Well, we're going to put in a negative 3 there. I'm going to have negative 3 squared plus 1. Now, if you put negative 3 and square it in your calculator, you should get a positive number. But I know that everybody's going to make this mistake because everybody makes this mistake. Put a negative 3 squared and negative 9. The calculator thinks you meant negative 3 squared. It takes care of the exponent first, and then it applies that negative sign. However, if you put parentheses, negative 3 squared, then you're going to get the right answer, positive 9. Now, you know that negative 3 squared is going to be a positive number. So even if you write this in here, you're just going to write down 9 on the next line, because I guarantee you, I know you don't think this way, but you really are smarter than this calculator. Okay. So 3 squared, we get 9, plus 1 is 10. And then negative 3. Well, that's weird. When I plugged in 3, I got 3 over 10. I plugged in negative 3, I got negative 3 over 10. That's the kind of symmetry we're talking about. Okay. If I plug in f of negative, or f of 2, okay, we're going to get 2 over 2 squared plus 1. It's 2 over 2 squared is 4, 4 plus 1 is 5. What do you think is going to happen when we put in negative 2? Well, we get negative 2 over negative 2 squared plus 1, right? So we get negative 2, 2 squared is 4, 4 plus 1 is 5. So we get negative 2/5 here, positive 2/5 here. Okay, I'm going to show you what this one looks like as a graph as well. We're going to draw the picture so you can see what this symmetry looks like. All right. So at 1, right, we have f of 1. We have 1 over 1 squared plus 1. 1 over 2. Okay. F of negative 1, you should be able to guess, right? It's going to be negative 1 over negative 1 squared plus 1, just 2. Negative 1 over 2. I put in 0 into this function, right? We get 0 on the top and something non-zero on the bottom. I don't care what it is, as long as I know it's not 0. But we got 0 there. Okay. So what does this look like? All right, we're going to call that 1. 1, 2, 3. Okay. So when x is 0, y was 0. When x was 1, we got a half. X was 2, we got 2/5. X was 3, we got 3/10. So this graph looks something like this. Okay. How do I know what it's going to look like on the other side? Well, it's symmetric about the origin. So let me sketch this in a light color. That'll be a light color. Okay, so I think it's going to be something like this, because I'm trying to see it from across the origin. But let's just double check. Okay, so we have 1, 2, 3. So x is 0 is 0. X is right here. Okay, and then I didn't really sketch this out right. Hold on, let me erase this little tick here. This is another thing I liked about the before times was I would use an eraser as like a measuring device to make sure my scale was correct. So here's halfway, and we have a third, and we have a 2/5. So we're gonna cheat a little bit, okay? But this is what we're gonna have. All right, and these are supposed to be the same side, okay? I know they don't look like the same. Pretend they match though. Okay. But that's what you're supposed to get with an odd function. If you know what the first quadrant looks like, if you flip it, you know what the third quadrant looks like. Okay, conversely, 1 and 3. If you know what the second quadrant looks like, you know what the fourth quadrant looks like. All right, because it flips around the origin. All right, there's a lot of functions that happen to be odd. So why do I need this? Like, because later on we're going to be graphing some functions, and it's going to be work to like get the values out of here. And if we could say, oh, it's odd, then we don't have to worry about the other side. We can just know what it's going to be without having to graph a bunch of points. We know what the negative side looks like. It's free. Later on, and I'm sure you're all going to get here, that when you take a class called partial differential equations, which is a class you take after something called ordinary differential equations. One of the ways of solving this is to divide your solution, or you divide your pieces up into odd parts and even parts of your function, and then you go ahead and deal with those individually, because it's easier to group the odd stuff with the odd stuff and the even stuff with the even stuff. So if you ever find yourself in that class, you'll bring that up again, like, oh, that's where this is important. All right. What about even? Okay, what about even functions? Okay, so all right. With even functions, they're symmetric about the y-axis. So whatever's going on over here is going on the other side. Conversely, if it's in quadrant 2 or quadrant 4, it's also in quadrant 3. Okay, if it's in quadrant 1, so quadrant 1 is the same thing that's going on in quadrant 2, or whatever's going on in quadrant 4 is going on in quadrant 3. Okay, so how about 1 over x squared? 1 over x squared is an even function. Let's see why that is. Again, if I plug in 0, I'm going to have some problems. Actually, let's do it this way. Let's not do that one. Let's do x squared plus 1. Then we don't have that problem. Okay, so when x equals 0, all right, we plug in the 0, we just get 1. Okay, how about 1 and negative 1? Let's pair them up. Okay, so when x is equal to 1, we have 1 over 1 squared plus 1. That's a half. When x equals negative 1, that's 1 over negative 1 squared plus 1. Well, negative 1 squared is positive 1. Positive 1 and 1, that makes 1 over 2. What if I pair up 2 and negative 2? I think at this point I have a feeling you sense a pattern. Okay. Oops. X equals negative 2. X equals 2. We have 1 over negative 2 squared plus 1. That's 4 plus 1 is equal to 5. So these are both a fifth. If I start to graph this, right, they're all positive, so I can just deal with this side of the graph. Let's call that 1. No, actually, let's not call that 1. Let's call that 1. Okay, so that's a half. So 0, we're at 1. When we are 1 away, then we are up to a half. 2 away, we're down to a fifth, which is down here. And 3 away, that's going to be 3 squared plus 1. That's still going to be 3/10. Okay. So we're going to end up with something that looks like this. All right. What do you think is happening on the other side here? All right, so it's the same thing on either side of the y-axis. You could fold it over and it will be the same. Okay, so there's a lot of functions that we use this symmetry to help us solve problems. Because again, if you know what it looks like from 0 to whatever, then you could flip it and you know what the other side looks like as well. So it's not quite as much work. All right. So the two statements that we're going to make about this is a function is even if f of negative x is equal to f of x. It's kind of like we ate the negative sign here, but all it means is it flips over on the other side and it means the same y value. The negative side has the same y value as the positive side. That's all this is saying. Okay, a function is odd if f of negative x is equal to negative f of x. Like the negative sign floats through. It doesn't, but it looks like it does. Okay, so let's see if we can come up with a nice, well, let's test, right? Let's test 1 over x squared, right? So we're going to say, well, what's f of negative x look like? What's it look like 1 of negative x squared? When I square the negative x, we just get 1 over x squared. Hey, the function looks like it ate its negative sign when I put it in there. They're the same. That's how we know this is an even function. Okay. How about x? Well, we did x over x squared plus 1, right? That's f of x. And when I plug in f of negative x, we get negative x over 1 plus negative x squared. This business here, that's just going to be equals negative x over 1 plus x squared. And it's kind of traditional that you would move this negative off into the edge here. So when f of x equals x over 1 plus x squared, f of negative x is equal to the negative part of that. So that's why we would know this would be odd. All right. I'll show you the problems that they have you do in the book. All of these were a lot harder than the ones they hand you in the book. So symmetry with the origin, oops, x-axis origin. Okay. Was that what they're going to ask? Really? Boring. Okay. Let's see, they ask me something useful here. Determine if this graph is even, odd, or neither. So look what's going on here. Okay. I also know which graph this is. You'll get to learn this shape in pre-calc or trig. But if I look at what's going on in the first quadrant, what's going on in the third quadrant, right? We're getting here, we're down here. We're here, we're down here. We're here, we're flipped over here. Okay, so this is an odd function. By the way, I was terrible at doing this stuff when I was taking classes. I did not like eyeballing this and trying to visualize it. That was really hard for me. I pretty much chalk that up to being a guy and not being able to have good pattern recognition that way. So, all right. Like I said, they give you pretty easy ones. Okay, like this one, like, both of the exponents are odd. I wonder if that's going to mean something. Okay, we should still test because you never know. There's times when they won't be. Okay, but we're going to say, okay, f of x is equal, or h of x, excuse me, 3x to the 9th plus 8x to the 7th. Let's see what's going to happen. So if we try f of negative x, we get 9 negative x to the 9th plus 8 negative x to the 7th. See, they're all out here. Negative x to the 9th, we have one power left over, right? We have negative x times negative x times negative x. We're going to do this 9 times. It's an odd number of negative signs. This is going to be negative 9x to the 9th. Same thing here. We have an odd number of negative signs. We're going to have negative 8x to the 7th, which is equal to negative, parentheses, 9x to the 9th minus 8x to the 7th. So this is f of negative x here. All right. So f of negative x is equal to negative 9x to the 9th plus 8x to the 7th, which is equal to negative of the original function, right? That's equal to the, oh, there was a, okay, what did I put 9 here for? What am I doing? This is a 3. I can imagine. Where the heck did that 9 come from? Yeah, because I was careless. Thank you for that. Yep, that's it. Yep, because I was too hasty and miswrote it. So that's what's going on. 3x to the 9th plus 8x to the 7th. This was equal to negative f of x. So we know this one is odd. All right. So we checked. And we said this is equal to negative. Can I do a parentheses? Am I allowed? No. 4 parts? Really? Are you kidding me? Fine. 3x to the 9th minus, what did they have? 8 x to the 7th. Usually, to try to trick you up on this, I'll make both of the coefficients even to see if I'm testing the right thing. But that's really about as hard as that gets. Okay, so it's negative. Can I do parentheses yet? No. 3x to the 9th. Okay. Minus 8x to the 7th. Okay, check. All right. They are equal. Good Lord. Function is odd. All right. So let's see what we have over here. So this one will be good because this will be a different answer. Okay. So we have negative 7 absolute value of x plus 5x plus 2. So let's try. Here's my f of x. Here's my f of negative x. They have negative 7, negative x, plus 5, negative x, plus 2. Well, the absolute value of negative x is just x. So this is negative 7x. But this doesn't do anything, right? There's nothing to simplify here. It's just minus 5x plus 2. How is this related to negative 7x plus 5x plus 2? Like, there's not a lot we can do there. So since f of negative x is not equal to f of x, nor is it equal to f of negative x, like, we're just done here. So neither. This doesn't have symmetry. Okay, that's all we can say. So what do we have here? We have negative 7 absolute value x. Okay, minus 5x plus 2. Part 1 of 5. Are you really? We're not doing the rest of that. Okay, they just want you to type in like what it is for negative and what it is for the regular one, and then we'll see. Okay. So here we are, piecewise functions. Okay, I think I told you this story before. Why don't I tell it again, just so that we're sure that something's happening here. Okay. So I apologize for hitting this to you guys again. But here's my piecewise function. Here's my story. So this is going to be the age of the child. And this is going to be their bedtime. Right. So the idea here is When I was a child, I had bedtime, and I loathed it. I hated having a bedtime. I wanted to stay up late. I wanted to watch TV. I wanted to see what everybody else was watching, and I was missing out on. So I had to petition. I'm the oldest, so you know, I had to break. I had to forge the rules. So you know, I'll say I'll probably start around age 6. I want to stay up late. If you guys have small children at home, you probably know this battle very well. We'll just, for the convenience sake, we'll just say 8 p.m. And 7, I ask, can I stay up later? No. Okay, 8 p.m. Can I stay up later? Yeah, we'll let you stay up late on your birthday. Okay, and then you can start staying up at, say, 9. Okay. So all the way, I don't know what the bedtime was before 6. I have no idea. Okay. But here, okay. Now, oops, this is age of the child. This is not PM, this is age. So the day before your birthday, you're going to ask them, like, hey, I asked for my birthday. Can I stay up extra? And I say, no, it's not your birthday yet. So we're going to go all the way up to the day before you hit 8. And 8 p, you know, when that child hits 8, they're going to say, okay, I get to stay up until 9. We agreed on that, right? I say, no. I'm like, no, we agreed on that. I'm staying up. Okay, you may not, you probably won't make it, but you know, at least the bedtime is now done. And until age 10, right, you'll be there. So what this is saying is that from the time the child is 6 to 8, their bedtime, 8 p.m. Okay. Once the child turns 8, they jump up, and now they can stay up until 9 p.m. And then again, you know, at 9, you ask, but like, no, we're not doing that. And at 10, you say, can I have a later bedtime? Okay. And then since that's working so well, right, we're going to go from 10, we'll go from 9:30. Okay, because you gotta, parents are going to start compromising with you instead of letting you have a whole hour because they realize they're running out of evening. Okay. And this will go on, right, until you're, I don't know, 14 or something. And then they just say, oh, you're in high school now, you go to bed whenever you want. But we're not driving you to school if you miss the bus. So you have to get up in time in order to make the bus, otherwise you're in trouble. Okay. So this is a piecewise function. And this is the mathematical way of saying that depending on who you are, you get different rules. Okay. Now, as adults, I won't say we're okay with that, but we've seen it enough in life to know that depending on who you are, you were afforded a different set of rules or a different set of laws than other people. Okay, it sucks, but you know, that is the way life is for us right now. So we're going to check the domain because that's who you are, and then the f of x, that's the rule that applies to you. Okay, so in math, right, we'll do an actual example here. We'll say s of t equals, we'll have 1.5t, and we'll have 50 over 9t minus 19. Okay, now there's no rule that says that these have to connect up. They often do, but just like life, we know, right? When you like make over a certain income, like there's a very drastic change as to which rules you get to follow. So this went from 0 to t up to 20. See, math, we tend to like it when things line up, but there's no rule that says that has to be that way. So if the dots don't connect, that's just the way it is. The dots don't connect. They will often connect. Okay, what is this? What are we talking about here? We're talking about sled accelerates down a hill and then slows down after it reaches the flat portion. Okay, speed of the sled in feet per second is the stuff. Okay, that makes sense, right? We're going to slide down the hill and it's going to go faster and faster and faster until we hit 60, until we hit 20. And then from 20 up to a minute and a half, who's staying on a sled for a minute and a half after it starts slowing down? I guess this person is. Okay, so after 20, we're going to start slowing down and see what happens. Okay, so determine the speed after 10, 20, and 50 and 90 seconds. Okay, So we're going to say t is equal to 10, 20, so is there 30 in there? 50 and 90. Okay, so who are you? Your t is 10. Okay, which rule are we following? Oh, t is 10 means we follow that rule. Okay, so all we're going to do is we're going to say s of 10 is equal to 1.5 times 10, and our speed here is 15 feet per second. Okay. At 20, we'll say s of 20 equals, and then we have to see like where, which rule are we in? Well, 20 gets to follow the stop rule still. Okay, so we're going to do, this is 1.5 times 20, and it looks like we're at 30 feet per second. And since we have this rule here that says, okay, well, 20, we're here, and then just the moment after you get 20. Okay, so I want one blink after 20 seconds. Okay, so I'm going to put in 20, even though I'm going to be like 20 plus a nanosecond more. We're going to put it in this one because I just want to see what happens. Because I put 20 in here. Did I get the right function? Yeah, I did. 20 times 1.5, that should be t times 15. That should be, oh, it's 30. No, it's 30. Okay, I don't know. I'll mark that. So 20 plus, okay. Just the plus. I want 20 seconds to go and then one blink later. Let's see what happens. So we have 50 over, I don't like this function, I don't think. We have, again, did I write the right thing down? Yeah, we did. I'm going to put 20 plus minus 19. Well, 20 minus 19 is 1. And then we're here at 50. That doesn't make any sense. I don't like this. I think I did something terribly wrong here because 20 times 1.5 you know what? Oh, no, that's right. It's 20 times 1. It's 30. I think they messed up. These should have, like, there's no way, right? We've all been on a sled before. There's no way. Once you get down to this, once you get to the end of the ramp, it's not speeding up by a ton just because you started going on the flat part, right? That doesn't happen. Like, to make that kind of a jump. So I will bet they really, I bet they, oh, but I know what happened. I will bet that they copied this from another problem. You forgot to check it. I'll bet that should be a 30. Let's make that a 30. All right. I wonder if it's that way in the answers. So it'll be 30. Your max speed after sliding down the hill. All right. And then we'll say 50. Okay, so S is equal to, we're going to say 30. I'm going to check it for both of them. I'm going to see if they change the answer to match this one or not. Okay, so we have 50 minus 19. Here we're going to have 50 minus 19. All right, what's 50 minus 19? I'm going to be terribly lazy today. This is awful. 50 minus 19 is 31. So this is going to be 50 over 31. And this is going to be 30 over 31. So after 10 seconds, what are we doing? We're moving 15 feet per second here. All right, 20 seconds. Now we're moving 30 feet per second, right? Because 20 seconds times 1.5 is going to be 20 and half of that. All right, they liked it. All right, let's find out. Let's go with 30 over 31. Oops. How come I can't write down a fraction? Did they say anything? Round to 1 decimal place. Okay, fine. So let's go with 30 over 31, 0.97. Actually, one decimal place, we're going to go with 1. No, I didn't like it. Go 50. Oh, that's a weird problem then. Because usually you have to check out the breakpoint, and at the breakpoint, it doesn't make any sense. It was 50 divided by 31 here. 1.6, which is, I guess, it's one decimal place. Okay, weird. I don't like it, but weird. It shouldn't happen. Like right after you hit 20 seconds, it shouldn't like all of a sudden jump in its speed like that. But all right. And after 90 seconds, we'll play by their rules. So 50, and what do we have over here? We have 90 minus 19. 90 minus, oops, 90 minus 19. 0.7. Okay. All right. Okay, but that's pretty much what you do for a piecewise function. Okay, is what neighborhood do I live in? What rules apply to me? What neighborhood do we live in? What rules apply? Okay. And generally if I do that for adults, they're pretty good about picking it up. When we have to do with high school kids, they still think life is fair. So I think this is going to go on to a point that I will warn you against, because x plus 3 for x less than 0, x plus 3, so when x equals -3, we're at 0. All right. So they don't have an endpoint on here. So x could be, wait, we could have x equals -4. It doesn't say that, once you've gone $3 in your debt, like you can't go anymore. I'm like, no, the door's wide open. You can go $100 in debt. We could be down here somewhere. So these are not going to be good because they stop how much debt you can be in. And this one says you be in debt for as much as you want. Oh, they're not going to do a part B. All right, well, let's go with that. Okay, the one thing that I'll warn you against is that a lot of students will see a piecewise function graph like this. Like say we have x equals, and we'll say f of x rather. F of x equals, we'll do absolute value of x for x less than or equal to 0, and then x squared for x greater than 0. Okay, so those are two fairly nice and easy graphs to deal with, right? I know nobody likes seeing the absolute value, but it's just a v. Okay, so when x is less than 0, right? Here's my absolute value of x. Okay, that's the absolute value of x. X greater than 0. Okay, so we live in a different neighborhood now. We got a different rule. Okay, but one of the things I always see, and this is one of those things, like you're not allowed to do this because they told you it was a function. If I draw this, right, just thinking, oh, absolute value, no problem. Is f now a function? And the answer, right, is no, it is not a function anymore because it fails the vertical line test. So they told you it was a function, and you've drawn me something that isn't a function. Okay, so this is not a good thing. Okay, so when you draw these things, try to make sure that you're dealing with a function, right? They're not going to overlap on the same domain area. Okay, so when you change neighborhoods, only one new rule applies. All right, you don't get to apply both rule and then pick. You only get to pick one rule. Okay, so just be careful about that you truncate what's going on with, where the neighborhood ends, and you have a new neighborhood to deal with. You have a new rule to deal with in that neighborhood. Okay. That's the big mistake I always see people make, is that they draw two of them here, and it's one of those things. I mean, personally, it drives me a little bit nuts to do that. And then, yeah, then we have to deal with that. Oh, good Lord, this is a terrible multiple choice question. Like, why is that? Because the domain says, the neighborhood says x has to be greater than or equal to 2. Which of these is greater than or equal to 2? Which one of these is not like the other, right? It's just this one is greater than or equal to 2. So there we go. There's very little we have to deal with. I know there's a lot more to this. I know we did this one then. Okay, because I remember doing this problem. Sorry about that. Okay, this is good. Where is it increasing, decreasing, and where is it constant? Okay, this is another thing. You can't look at the arrows. You have to look at what the function is doing. Okay, the arrows only serve to lie to you. Okay, so when a function is decreasing, right? So okay. So if you imagine somebody is skiing on this function, this is like a cross-country ski kind of a thing. This person, I would not suspect that this person is having a lot of fun. So this is where the function is constant. Constant's not that bad. Everybody gets constant. It's this one that people don't get, because they'll see something like that. They're like, oh, it must be increasing. Like, nah. Every time you put your little person right on your graph, if they're skiing and they're having a good time, even if it's terrifying, this is a decreasing function. Every time that skier is doing work, that's an increasing function. Okay, every time it's just like, just a regular day cross country, then it's okay. But I see a lot of functions that get written, things like this, right? When they have these crazy things, something like this, and somebody will look at this and they'll say, oh, it's increasing because that's where the arrow's pointed. I'm like, nope, put your little person there with the skis on. This is a terrifying experience, but it's more fun than doing this way. By the way, it always goes from left to right. Okay, the ski always starts from over here for as much as you can. So since this person's having a good time, then we have a decreasing function. We bottom out, we have a moment of it being constant, right? And then it's back to work. So it's an increasing function here. Then we have a moment of zen here, where we just are constant, and then we're back here, decreasing. Okay, moment, and then we're increasing. Okay, I know it's a really simple concept, and I'm sorry I spent a lot of time on it, like more than 2 minutes. But it's also one of those things where when students get this wrong, I honestly do feel bad for them. I'm like, come on, this was the easiest one. And I know increasing and decreasing. I know. Again, if you put water on it and the water runs downhill, then well, no, because I don't want to say it, because this way, it's not going to work that way. Let's not go with the water. Let's go with skis. Okay, but it's one of those things where I know uphill and downhill. If you bike, I know you really know uphill and downhill, and it bugs me when students get it wrong, because I'm like, you should have had this one. You should have had it. So intervals on which it is decreasing. Well, this is a fun ski thing, if terrifying is fun. So let's see here. The function is increasing on the interval where? Okay, this is not a fun ski trip right here, at least to me. Okay, so x it looks like greater than 1. Okay, so it is increasing on the interval. Really? 1, and then off to infinity. It's always increasing. Well, not always, just increasing here. Okay. Where is it decreasing? Well, go back up here. It's decreasing between -3 and -2. Decreasing on the interval, -3, and do we say -2? -2. Yep. And again, parentheses, we didn't quite include that. Now, where is it constant? Okay, where is it constant? It's constant between -2 and 1. Are they going to let me do it? No, they will not. So we want -2, -2, and 1. All right, very good. All right, so that's increasing, decreasing. Again, it's one of those questions where, like, I really wish I didn't even have to ask, because it's the only time I catch people is when they're like, "Oh, I wasn't thinking about it that way." Like, I know, I'm sorry. So I don't like to take points off for that, because I know you know. So it's always a fun ski trip here, so it's always decreasing. Okay. Why do they do that? Function is always, oh, it's never increasing. It's always decreasing. When you say always, you'd think, right? You'd think you could put this, we put it in for you or something. Like, really? Oh, we're not done yet. The function is never constant. Okay. Tell you what, why don't we call it for the night? Looks good. And we'll pick up here. I'll try to do a couple more piecewise functions for us, because those are always fun. Those are the things that students have the most problem with. And we'll make sure we cover the rest of this stuff, and then maybe we'll go on to the next section, but there we are. Okay, let me go ahead and do this. So good night, everybody. Oh, not good night to the people that are right here.